Hello everyone and welcome to the basic course of Compact PLC IQ-F. The first Compact PLC for Mitsubishi Electric was born in the early 1980s, and more precisely in 1981 with the F series. This PLC evolved over the years until 2015 where the FX5U series is launched. What changed from the previous model is the speed of the processor. A fundamental feature of FX5 is the new high-speed bus that significantly reduced the cycle time. This bus allows to exchange variables with the smart modules on the right of the PLC 150 times faster than FX3U series. Let's go into a little more detail and let's talk about technical characteristics. Starting with FX5U and FX5UC models, let's see the programming languages available. We have by default as a standard languages the ladder, the structured text and the function block diagram or FBD. However, you will have the possibility to program your PLC also using the SFC languages only if you have a certain firmware version. As for programming capacity, by default, all PLC are set to 64K steps, and with a certain firmware version, it's possible to double this capacity. Note that by doubling the programming capacity from 64K to 128K, the cycle time is also doubled. The PLC itself exchange time. By increasing the programming capacity to 128, you also have the advantage to increase the number of local and remote IOs managed by the CPU. Technical characteristic of FX5UJ model. In this case, there are only three programming languages, the ladder, the FBD, and the structured text. The programming capacity is fixed at 48K and cannot be increased, as well as the number of I/O managed by the CPU, both local and remote. Now let's talking about the hardware of the CPU and what's on board of various PLC models, starting with the FX5U. On board there is an Ethernet port compatible with CC-Link iField Basic, an RS485 port, two analog input channel, one analog output channel, and a slot for a memory card SD. The program and the retentive memory are buffered by flash ROM, and by installing an option battery, you can increase the retentive memory area. On the PLC can be also installed expansion on the right side and on the left side, but also one expansion on board on the CPU. For the FX5UC model, there is one Ethernet port compatible with CC-Link iField Basic, one RS485 port, and a slot for a memory card SD. The program is also buffered by a flash ROM memory. The expansion can be installed only on the right and on the left side of the CPU. For FX5UJ model, on board we have an Ethernet port compatible with CC-Link iField Basic, a mini USB port for programming, and a slot for a memory card SD. The program and the retentive memory are also buffered by flash ROM memory. The expansion can be mounted on the right side, on the left side, and on board the CPU. The PLC coding. What is the PLC code made of? The first part is the PLC family, where we can find FX5U, FX5UC, FX5UJ. Immediately after, we find a number, the number of the total of input and outputs on board of the PLC. After that, we find the letter M, that means main unit of the CPU. After the letter M, we find a letter or a T or a R. If we find the letter R, it means that we have relay outputs. If we find the letter T, it means that we have transistor outputs. These letters are followed by a slash and a letter that can be an E or a D. If we find a D, our PLC is powered by 220 volts. If we find the letter D, our PLC is powered by 24 volts direct current. Finally, we find the indication of the known transistor PLC of the logic of the transistor. If we find a single S, it means that our PLC has transistor output with NPN logic. If we find a double S, it means that the transistor output is PNP logic. The rules are also applied to other two types of PLC, the FX5U and 5UJ and 5UC. Here we see the models of CPUs and module that can be installed on the various CPUs. But let's talk about the rules for a correct hardware configuration. Let's start with the expansion board that can be only installed on FX5U and FX5UJ. For both of these PLC, you have the option to add an extension board mounted on front of the PLC on the CPU itself. For the left side extension, there are different rules for FX5U and 5UC and FX5UJ. On FX5U and 5UC can be mounted 6 modules that are divided in 2 communication adapter and 4 analog adapter. In FX5UJ, we can connect only 4 modules, and there are 2 communication adapter and 2 modules. If there is the extension board mounted on the CPU, can be installed only 1 communication adapter. Finally, we will talk about the modules that can be installed on the right of the PLC. Call it extension modules. As for the PLC, FX5U and 5C, you have the option to installing up to 16 modules on the right of the PLC. Within these 16 modules, there are some restrictions. In fact, a maximum of 2 modules can be installed for expansion of the power supply. 1 connector conversion module, 1 extended extension cable, and 1 bus conversion module. Also remember that the count of 16 modules, you must also take count the addition of I/O modules. As for FX5, the 5UJ has a total of 8 modules that can be mounted on the right of the PLC. Within these 8, there are still restrictions. In fact, it's possible to add a single module for expansion the power supply, a single connector conversion module, and a single extension cable. Again, for a total of 8 modules, including the additional I/O modules. Still in the field of the configuration rules, we must talk about the total number of I/O that can be managed by the CPU. Let's start with FX5U, which can control a total of 512 I/O points, including the number of I/O delivering from extension modules, which can be a maximum of 384, and from the remote I/O, Note that in the count of the remote I/O points, those that communicate with the CPU must not be considering, using the communication protocol CC-Link I feel basic. As for the power supply of the expansion modules, it is supplied directly from the CPU, from the power input-output modules, or from the power extension module. The number of expansion modules that can be connected to the CPU must be therefore also determined by capacity of the power supply. As for the FX5UJ, it can be controlled a total of 256 I/O points. In these 256 points, delivering from extension modules and from remote I/Os. Also, in this case, the I/O remote that are connected to the CPU using CC-Link I feel basic are not considered in the calculation of the I/O remote points. To facilitate the configuration of the PLC FX series, there is a configurator that you can find online on our website. And this allows you to select the desired CPU and additional expansion module. For each module, if it's a power input module, you will have the indication of the numbering of the power inputs. If you have, on the other hand, an intelligent module, the ID of the module itself will be identified. You always have the amount of I/O that can be managed, both physically and remote, and the amount of I/O used under your watch. In addition, you have the indication of the remaining power supply. In the case in which the maximum number of expansion modules is reached, it will no longer possible to add modules. In fact, the add button on the right disappears. In the case in which the maximum number of I/O can be managed by the CPU is reached, you will be notified via pop-up, as well as if the power supply is not sufficient. Summarizing, what do you have available with the configurator? We have the hardware dimension, the address of the special module, the address of the I/O, and finally the list of the materials for the order. We have also the amount of I/O managed and remaining. Let's talk about the CPU hardware, starting from the assignment of I/O. The assignment of I/O is carried out using a numerical system. The input are assigned to the X devices and the output to the Y devices. The address is assigned to each additional I/O module based on assignment made by the previous module, following the incremental logic. Therefore, from X0 to X7, the next row will be X10 to X17, and so on, for both inputs and output. The less significant number of the address of each module always start with 0. The last important note is that the assignment of I/O is fixed. It depends only on the order in which the modules are inserted into the configuration. In the example we see on the slide, we have a CPU FX5U32. This means that the CPU has 16 inputs and 16 output on board. The input are numbered from X0 to X17 and the output from Y0 to Y17. The first expansion module added on the right of the PLC is an FX58AX module of 8 inputs. The numbering of the inputs continues with respect to the CPU. In fact, its numbering is X20, X27. As well as for the second module, which is always a module of input, those numbering continue to the previous one, and it's x30, x37. The third module, in this case, is a module of outputs. The last object that used output was the CPU. Therefore, its numbering will continue respect to the output of the CPU. And this, therefore, is y20, y27. The next two modules are always output. Respect to the output module that mounted, they will be y30, y37, and the fifth is y30 and y37. The sixth module and last, in this case, is a mix of 8 input and 8 output. The input will contain their direction from the second module, which was the last one with input on board. So the inputs numbering are from x30 to x37, and the output will continues and will be y50 to y57. The CPU automatically assign a unique number ID to the intelligent module or bus conversion in the order of how they are installed in the system, from left to right, from 1 to 16. Module addressing is not performing for the following type of expansion: I/O modules, expansion board, expansion adapter, connector conversion module, connector conversion adapter, extension power supply modules. Now let's move on the wiring of the inputs and output of the CPU. In general, the inputs of the CPU or an I/O module can be both in sync logic or source logic. The difference is only made by the wiring. In any case, from the specification of the CPU or the single module, it's possible to verify what type of wiring is allowed. As for the choice of the wiring logic, it is made by means a pin present of the CPU. It is the S bar S pin. If the SS pin is both 24 volt, it means that we in input need at 0 volt to close the circuit. In this case, we are wiring our CPU in sync logic. If the SS pin is both 0 volt, it means that we need a 24 volt to close the circuit. Therefore, our CPU will be wired in source logic. It is more important to note that for the same unit or for the same CPU, it is not possible to use a mixed logic. As for the output, we actually have three cases based on the types of output present on our PLC. In this case, the wiring logic is chosen at the time of the purchase. Or either, for the PLCs known in relay, you can choose the wiring logic for each group of output. In fact, the PLC has grouped output that are share the same common, based on the potential of reference that you connect to the common pin. You choose the wiring logic for the group of the output. As for the PLCs known in transistor, the wiring logic must be chosen at the time of the purchase. In fact, there are PLC with transistor output in sync logic, MPN, and PLC with transistor output in source logic, PMP. Speaking of the hardware that we have on our PLC, let's now have a look to the characteristic of the Ethernet port. The feature of the Ethernet port that we find on board on the PLC are the direct communication, which can connect the CPU directly to the PC, therefore to Works3, with an Ethernet cable, without using an hub. Using the direct communication, it's not necessary to know the IP address or the name of the CPU, which you must communicate. Therefore, PC and PLC in this case can also be found within two different subnetworks. Attention, I repeat, to use the direct connection, the PC and PLC must be connected directly via an Ethernet cable, not from an hub. The SLMP server protocol is available, which is used to respond to command from SLMP client. The predefined protocol, which allow you to exchange data between the CPU and external device, such as measuring instrument or a barcode reader. The socket communication, which allow you to communicate with external device on Ethernet basis via TCP or UDP using socket communication instruction. Modbus TCP, which you can read and write devices area connected via Ethernet. FTP server, by using the FTP dedicated command, it is possible to allow an external device to read and write and delete individual file of data within the PLC. SNTP client, that possibly to query a SNTP server connected to the LAN, using it to synchronize the CPU time whatever the server is. Web server functionality, by which it's possible to perform CPU diagnostic, monitor, and read and write devices. CC-Link I Basic Communication Protocol, which the PLC can both be master and slave of this network, and then I dynamically change the CPU IP address. Up to 8 simultaneous connections are allowed, plus a MELS of communication on this port. The MELS of connection is the one that allows the PLC connect to operating panel, but it's also the same connection using by Works3. The CC-Link I Basic, the FTP server, the NSTP client, and web server are not included in the number of connections available. For the serial communication, not only for the built-in port, but also for the port from the communication adapter, there are different type of communication. The MELS of communication, which allow you to communicate with PLC, with a PC, or with an operating panel. The end-to-end network, which puts up 8 PLC of the FX5 or FX3 series in communication. The parallel link, which allow you to communicate two PLC of the FX5 series. The MC protocol, which is communication between the CPU and external devices. The inverter communication, which give you the possibility to command with the FX5 up to maximum 16 inverters. The non-protocol communication, to communicate with external devices such as barcodes, printer, or measuring instruments. The predefined protocol, therefore the predefinition of appropriate protocol to communicate with third-party device. And finally, the Modbus RTU, which can be used both as master and slave, and which give you the possibility to control a slave with 232C connection and up to maximum 32 slave with 485 connection. We are still talking about the hardware of the PLC, and in this case of the FX5U, which has 2 analog input channel and 1 analog output channel on board. They are all three 10-0 volt with 2.5 millivolt resolution. To read the 2 input channel, there are 2 special variables, the SD6020 and SD6060, as well as to write the analog output, whose digital value must be written inside the SD6180. The PLC FX5U is designed to handle only the voltage inputs. However, it's possible to use the input even in current at 20 mA, connecting between V plus and V minus. Terminal of the analog input self a resistance of 250 ohms. In addition of the normal IOs, the CPU can also have high-speed inputs and output. As for the input, we have up to 8 interrupt inputs available. These are the first 8 CPU inputs from x0 to x7, which by simply setting a parameter become high-speed inputs. These inputs can be used as interrupt inputs, fast counters, where we have up to 6 with a count of 200 kHz and 2 at 10 kHz. For the X5UJ, we have 4 at 100 kHz and 4 at 10 kHz. Or they can be used up to a maximum of 4 PWM inputs. As for CPU with transistor output, we also have high-speed outputs on board. And we have up to 4 PWM or up to 4 200 kHz position. The FX5UJ in this case has only 3. As for the inputs, even for the output, it is always the first 4 or 3 output, which by setting a parameter become normal output to high speed output. Now start the second part of the iQ-F course, and here we will talk about the software of Works3, the memory of the PLC, its devices and the labels. The software Works3 can be used for programming PLC, iQ-F and iQ-R. The development environment is composed of several menus. Some of them can be positioned as best as they retain around the screen, or can be also closed. To ensure backward compatibility with the past, the Works3 is able to read project created with previous software. To do this, you will need to select the open order file format in the project menu and select the software which the project you want to import has been created. The programming languages are 3 plus a fourth, that is the SFC, available only for FX5U and FX5UC. The 3 basic programming languages are available on all CPU, and they are the ladder, the ST, and FBD. The 3 programming languages, or rather 4, cannot be used simultaneously within the same program block, but it's possible to structure a project by dividing it into different program blocks, and each program block can be in a different program language. Another thing is that is not possible to convert one program into another language. So if I have a software written in ladder, I have no way but rewrite it to become an FBD or ST. To create a new project, from the project menu, once Works3 is launched, I will select New and indicate the series of the PLC and the type of project. The choice of programming languages is not binding. In fact, the software can be composed of different program blocks written in different program languages available. Choosing the program language when a new project is created is only need to allow Works to create the first program block. Once a new project has been created, the project tree will also be made visible. Let's see now what the project tree consists of, starting from the top. The first option, we find the module configuration, which is nothing more than the graphical representation of the hardware configuration. Immediately below, the section linked to the module configuration, we find the one linked to the program. Inside the program folder, we find a whole series of subfolders that correspond to the execution types, therefore to the ways in which the PLC run and the program insert into this folder. In each execution type it provided, we will find a program file, therefore the container of the program blocks. The program file will be composed of different program blocks, which are made up of the program body, which is called program body in the case of ladder language, or workspace in the case of ST or FBD language. To each program body or workspace, that is, its folder of local label will be associated. Local label that can be used within the program block. Finally, we find the section linked to the unregistered program. We will then see the difference between the execution type folders and unregistered program. Below, we have the area of the function and function block, followed by the section related to the labels. In this case, we are talking about global labels, the common to the entire project. The section related to the data structure, also in this case we will find the data structure of the program. We find the section related to the devices with the comments associated with the individual devices. The device memory, which is nothing more than a table of variables containing the associated values that can be read or write from CPU. And the device initial value, a table of variables containing the value that can be set within this variable at the CPU power on. Finally, we find a section related to the system and CPU parameter. Within the CPU parameter, we also find all parameters related to the hardware of the CPU itself. Therefore, Ethernet port, serial port, input and output, rather than analog input and output, or all the parameters related to the options that are added to the PLC, on the left or on the right. Finally, the last section of the project, there is the one related to the remote password, where it's possible to set a password by which the access to the CPU is limited. As first thing, when the PLC is programmed, it's good to perform the hardware configuration of the system. Within the configuration module, you will have the possibility via the element selection menu to insert all the expansion module present in your hardware configuration. So, as the first thing, it will be essential to set exact CPU model that you have and add the expansion module to the left and to the right. To complete it, it's necessary to perform a parameter fix. Now let's talk about the memory of PLC FX5. You see here the list of all the devices available, but we will focus only on some of them. Let's start by talking about input and output. As we said, they are called X and Y, and fundamental they are number in octal numerical system. In input are used to read the state of the physical connected to the inputs, while the outputs will be used to manage the external object. Another device of type bit present in the memory are the AMs. It's a memory area where it's used as an auxiliary relay within the CPU. There are normal AMs and rotation AM. The normal AMs are reset at the CPU shutdown, while the rotation AM remain their value even after shutdown, and to delete them, a latch clear must be performed. The entire M memory area is a user memory area, so there are no special M. Then we have the L, which are nothing more than auxiliary relay, in this case retention. All L maintain their value even after CPU shutdown. Then we have the link device B and SB, and there are type bit, and then V and SV are of type word. These are devices that can be used to refresh data with a network module present within the system. If they are not used for this purpose, they can be desired as the program within the software. Then we have the bit of type F. In this case, It's a memory area, also bit, used in the program by the user to detect the error or glitches. The step relay, called S, are bit devices used to perform automatic step cycles. They can also be used for other purposes. Then we have the timers. They are devices that perform the time measurement from the moment the timer coil is activated. The contact with the timer is activated when the time passed reached to the set point. There are normal timers and retention timers. Normal timers are called T, retention timers are called ST, and they maintain the value over the time even the enable condition is missing. Regardless of the fact that they are less retentive, the timers can be classified into low speed timer and high speed timer. The difference between these types is determined simply by the PLC instruction used. To use a low speed timer, the out instruction must be used. To use a normal timer, the OUT-H will be used. To use a high speed timer, the OUT-HS will be used. Then there are the counters. They are devices that count the numbers of time the input condition in the program are verified. The counter reaches the logical state 1 when the counting value reaches the set point. There are two types of counters. The difference is not if they are less retentive, but the range of counting. The counter C count to one word. The counter LC count to two words. Finally, there are the register called D. It's a memory area in Word that can use in the program to process digital data. It's possible to point the bit of each device. In addition to the user device, there are also system devices. System devices have fixed capacity and allocation and cannot be modified by the user. There are special bit memory area called SM and special word memory area called SD. The special bit are SM400, which is the bit always at 1, SM401, which is the bit is always at 0, SM402, which is the bit of the first scan, or all clock bits, such as bit 409 to bit 413. As for the special memory area, the word type we find, for example, SD201, which indicate the state of LEDs, SD520, which indicate the times of scan of the PLC, as well as the SD, which allow you to read the analog input and write the output of the FX5U. Since they have pre-established function, the special memory area cannot be used within the program as user memory. How is the memory configured? The memory of the PLC is divided into two sections. The data memory, which contains the file related to the program, the FB, the parameter, and the comments, and an area dedicated to the devices and the label, which is the internal memory area, where the devices and label are contained. The devices label memory area is divided into two, a standard memory area and a fast memory area. The difference between the two memory areas is certainly the size of these two areas and the speed with which the PLC is able to question the devices contained in one area rather than another. Therefore, the PLC will be less likely to question a variable contained within the fast memory area than a variable contained within the standard memory area. What do we do inside the fast memory area compared to the standard memory area? First of all, the standard memory area also contains the label and the rotation label, while in the fast memory area only the devices normally used for programming are contained. we find the input and output, the M, the word, the counters, the timer, and so on. For each memory area, you have the possibility to choose the retention range. In the standard memory area, however, we find only the variable R, W, and SW. Another difference between the fast memory area and the standard memory area is that the fast memory area has the default retention range, while the standard memory area becomes retentive only if the tampon battery is installed. Otherwise, the devices contained within this memory area are not retentive. Another substantial difference between these two memory areas is their capacity. Where the standard memory area has a capacity of 48K words, the high-speed one of 12K words. You also have the possibility to choose which of the two memory area to place your label. Remember that the total sum between the devices of the same area, the label and the retention label, can never exceed 48K words in the case of choosing the standard memory, and 12K words in the case of choosing high-speed area. What is a label? A label is a string of characters that identify a memory of the PLC. It is possible to define labels by associating them univocally to an absolute device or leaving the association to the compiler. So, automatically the PLC allocates the device to the spare memory area. In this case, we are talking about self-assignment. Devices and labels can be used in a mixed way within the program. The string that identify a label cannot start with a numerical character, and the reserved word for a special character cannot be used. Labels are classified into two types, the global label and the local label. Global label are variables that can be used in the entire project. Local label, on the other hand, can be used within the pool to which they are assigned. Another substantial difference between global label and local label is that local labels are wholly in self-assignment. How do I create a label? First of all, I define the string that identifies the label. Then I choose the type of data among all those proposed. I define the class of label. If I want, I set the association between the label and the absolute device for global variables. And optionally, I can insert a comment. The type of data available are those we have seen so far. We have bit, word with and without sign, double word with and without sign, real-time variables, timer, string, retentive timer, 16 or 32-bit counters, and pointers. The only type of data that doesn't exist in the Mitsubishi Electric PLC is the byte. Of all this type of data, you then have the possibility to define arrays that can have a maximum of 3 dimensions. Now we start the third part of the course. In this section we will talk about the type of execution of program. We will do some program tips, and finally we will conclude with the debug tools of Works3. Let's start by talking about the type of execution program. From the project tree, it's possible to visualize and set the execution model of the various programs present within your project using drag and drop. The same setting can also be executed using the CPU parameter. More precisely, you will need to open the CPU parameter in the project tree, enter the program settings section, then enter the setting program and select its execution mode for each program. Starting from top, from how they are shown within the project tree, let's see what the type of the execution program are. The first proposed mode is the one called initial execution type. Programs of this type are executed for a single PLC scan. Then it goes from the stop state to the run state, and therefore also to the power of state. Immediately after executing the program present within the initial task, the PLC will start executing the program present within the scan task. This program are executed once of each PLC scan cycle. So, as soon as the execution of the program in initial is completed, the PLC will start executing a cycling manner everything that is contained within the scan task. Another type of execution of program is fixed scan. Programs inserted within the task are executed at an interrupted time interval. Unlike the classic interrupt program, these do not require the use of interrupt pointers. It is possible to insert up to 4 programs within this task and assign a different interval to each of them. There are also event programs, which are inserted into the task called event. This execution of this program is triggered by an event determined by the user. The event can be interrupt pointer, any bit of the CPU, or a passing of time. The example below uses an interrupt pointer. The program is executed instantly when the specified interrupt conditions are met. At the end of execution of the interrupt, the CPU will continue to execute what was contained within the scan task. The interrupt program is enabled with a bit of the CPU. The bit that can be used for this function can be found in the table below. The program is enabled with the elapsed time. The program is executed each time the specified time is passed. Standby type. These programs are executed only when there are a request of execution. The last type of execution of program are no execution type and they are registered program. In both cases, the programs inserted into these two types will never be executed by the CPU. However, the programs that are inserted into no execution type are compiled by the software, downloaded into the CPU and saved in the memory, even if they will never executed by the PLC. If, on the other hand, a program is registered within the registered program, in this case, the program is not downloaded into the CPU because it's not compiled. Let's talk about programming now and see how a project is structured. A structured program is composed of several components divided according to the information processed and function performed. The project is usually composed of several program files, which are made of one or more program blocks. Program blocks can make use of POUs, Program Organization Unit. A POU can be a function block or a function. A single project can be downloaded on a CPU. The project is divided into several components, but at the end, it must be a single project. Because on a CPU, it's possible download only a single file at a time. Finally, the order of execution of program and POUs can be defined by user, as we have already seen previously. What is a program block? A program block is a unit of a program. Each unit is designed to have a high degree of independence from the rest of the program. To allow easy substitution or addition, a program file can be composed of several program blocks, and the order of execution of latter can be decided by the user. Why is convenient to divide the program blocks? Because it makes reading the modification or substitution easier. Program blocks are finally memorized within the program file of each program. How to create a program block? Right-click on the program block and select the type of execution you want to give it. Right-click on the scan task, select Add New Data, and then define the name of the associate with the program block. Select the programming language and confirm the type of execution of the program block. At the end, click OK, and the program block will be inside the selected type of execution. Right-click on the main and select the order of execution of the program block. Once the program block is created, it will be possible to start editing the program. To edit the program, you can proceed in different ways. For the basic instruction, such as contact coils, contact normally open or normally close, and inputs, you can use the toolbar or the quick selection keys. For example, the key F5 is a contact and F7 is a coil. The third and the last way to insert graphic object is to use the bar at the top of the menu. More precisely, you will use the edit menu and click on add element, the add symbol. In this case, all symbols will be displayed in form of list. As for the instruction, you have two options. You can use the element selection menu, in which you will find all the available instruction divided by function. Simply by dragging the selected instruction into workspace, it will be added. If you know the name of the function you want to use, you just need to position yourself inside the worksheet and start typing the code from the keyboard. The list of the available instruction will appear, whose name matches with the one you have entered. By clicking OK, the instruction will be inserted. For each instruction, you can use the help online. There are two ways to start the help online. You can select the entire instruction and press F1 key on the keyboard, or as shown in the figure, using this button with the blue question mark that always appears when selecting the instruction. By clicking on the help online, the Emmanuel Viewer software will be automatically opened. You will be brought to the instruction manual page, and you will have the necessary information for compiling the instruction. How do I create a label? To create it quickly without going to the table of label in advance, you can also do it directly during the writing of the code. First of all, I have to write the label I want to create from the keyboard. A pop-up will open, which is what you see below. This is a pop-up for editing labels where you will need to define the type of label. So whatever local or global, the class, the type, and optionally a comment. The only thing you can associate with the label in this pop-up is the device, in case of creating a global label. All you have to do is to point to this indicator where it say open the label editor and will appear automatically. You will be automatically brought to the table of global labels where you will then have the possibility to associate the device with the newly created label. In this case, in which the label was already created, without having to create a new one, it can be called directly from the worksheet by simply editing it. So I start writing his name with the keyboard associated with a contact to a coil, and it will appear within a list of existing variables. Once the code has been written, before it can be downloaded into the CPU, it must be compiled. The compilation is used to verify the errors have not been committed before the download. You can compile using the key on the toolbar or by accessing them from the convert menu. There are three compilation modes: the convert execution, the compilation of the single code and label edited from the last compilation successfully executed, read bit all executed, the compilation of the entire program, and the label of the project. And finally, there is the possibility to run an online program change, which execute the online changes on the CPU if errors are not detected, even if it is in run. If errors are detected, following the compilation, they will displayed in the output window, and simply by double-click the error, you will be sent back to the part of the code that caused the error. After successfully compiling your code, it's necessary to configure the connected between PC and PLC before downloading. In the Connect destination menu, it's possible to create different type of connection to the PLC, and of course rename them. The connection present in the current connection is the one currently in use. To change it, you can simply drag and drop the one you want to use. You have two connection options between PC and PLC: the direct connection or the other connection method. The direct connection is used only when PC and PLC are connected directly to each other, without use an hub. In this case, it's not necessary to set the IP address of the PLC and the IP address of the same class in the PC. So just double click on the direct connection to, to CPU button, select the network adapter and use to run a connection test. If the test is positive, you can proceed with the download. If the connection between PC and PLC is not conducted directly, but it is conducted by an hub, it's necessary to select the other connection method. Double-click on the PLC icon. You will need to enter the IP address of the CPU, which you will want to communicate. The IP address of all PLC FX files is for default 192.168.3.250. At this point, you can proceed with the download of the project. The download, you can do it via the quick selection button or via online menu, right to PLC. Select everything you want to download into the CPU. Normally, the parameter plus program selection is used and run. At the end of the download, you will asked to reset the CPU. It's essential to proceed with the CPU reset only when the parameters of the same are changed in order to make them effective. Once your monitor is present in the CPU, it will be possible to connect to it and monitor the operation. To start the monitor, you can use the quick selection button via the online menu. Select the monitor function and enable the program monitor with start monitoring. Now let's talk about the debug tools, starting with the cross-reference. The cross-reference returns the list of the device or the label used with additional information, such as if the device or label is used in reading or writing, the type of the data, the program block in which it is present, and etc. The cross-reference can be executed from the entire project or only from the desired program block. How to perform the cross-reference? Through the right mouse button directly above the device or label of which you want to perform the search, or through the Find menu, selecting cross-reference and entering the name of the device or label to be searched so far. So you can edit the device or label directly, and the user can decide which information to display in the cross-reference window. By right-click on the cross-reference menu, you can view the necessary information. Another tool for debugging is the device list, which is nothing more than a list of the device in the PLC with the indication of those used. How to open the device list? By clicking to the Find menu, select Replace, you will find the device list. In this case, it is also possible to perform the search in the entire project or only in a specific program. Watch tables are variable tables. There are a maximum of 4 which can be composed by the user, through which it can be possible to monitor and modify the state of the variables. Watch tables can also be used in simulation to interact with PLC project. how to open them from the view menu, docking window, and all 4 available watch table, or through the button with the I symbol. Open the desired one. Then register the variable within the watch table. To start monitoring, it will be necessary to right-click on one of the variables in the table and click Start Watching. For each device, it's possible to select the viewing format. How to change the state of the bit? As for the bits, you can change their logical state with 0 to 1, or true or false, or with Shift Enter on the keyboard. It is possible to import and export a set of data from watch table in CSV format. Note that with the CPU in their state of run, the code always has priority over the forcing you have done on the watch table. The modify value register to watch function does nothing but register the value that I have selected directly from the project, and I have the option by right click on it to modify the value. In this case of bit or registers, it within a watch table to monitor it and verify the value. The last tool for debugging is the device buffer memory batch monitor, which give you the possibility to monitor consecutive device on a single window. What is the find function? With find, it's possible to search within the entire project or a specific program for a device, a label, an instruction, a counter, or a coil, or a string. PLC diagnostic, it's possible to monitor the state of the PLC directly from the toolbar, from which you also have the indication of the CPU cycle time. If, on the other hand, you want an indication of the current error code, or you want to verify consult the alarm history, you just need to open the diagnostic menu and click on the diagnostic modules. In the case of an error in the CPU, with the error jump button, you will be brought back to the code part caused the error. Finally, the simulation. From the debug menu, you can start the simulator to test the logic of the PLC. The PLC simulation can also be connected to the simulator of the Mitsubishi Electric operating panels. The simulator can be launched from the debug menu, simulation, start simulation, or through the quickest selection button. The watch table are always used for interaction with the simulator. The last tool for debugging is the manual viewer, which is nothing more than a software containing all the manuals. As we have seen before, it also acts as an online help in case you don't know or want more information about instruction. The manual viewer connects to the internet and automatically download updated manuals or new manuals not presented in the archive. Thank you for following the course. See you soon.